Okay. All right. So we are on the last section. So get the theorem page. We're going to be looking at that as we answer the first 5 or 6 questions, and then I will take you to the graphing. We're doing the graphs in this section of the other 4 trig functions, because so far what we did was sine and cosine graphs. That was in 6.4. And in this section we're going to do secant, cosecant, tan, and cotan. I did give you some patterns for secant and cosecant, but if you want to not memorize those patterns, I could show you how, just to, because you guys already have so many formulas to memorize, so to avoid memorizing those 2 extra patterns, I'm gonna show you how to graph it right off of the sine and cosine graph, because you can build the secant and cosecant right off of that. So we'll do that little shortcut for cotan and tan. You're going to have to memorize those 2 new patterns. So let's start by looking at what they look like ahead of time before you start building them yourself. Let me get a clean copy of the problems. Okay, so these graphs were also in the in section, I think 6.3 I gave them to you. I was trying to give you a look at all the different graphs, because in 6.3 they wanted you to start remembering how to talk about domain and range. So they were in that section, and I copied them again for you here so that we can see how they relate to the questions you're going to be asking. So be looking at these pictures. We already discussed them in section 6.3. But some things that you're going to have to know, like these, yes, I did give you a pattern for this and this. But I can get you to do those problems just by knowing the 2 patterns that you've probably already memorized for sine and cosine. That way you don't have 2 extra ones here. So we're going to do, see this little dashed line that you see right here? Since this right here, let's see, this is the cosecant graph. This is a cosecant graph, and do you remember that cosecant is reciprocal to sine? So what you're really seeing here is like a little auxiliary line, and it's really just a sine graph. It will be much easier than you doing the pattern, because all you'll do is for the asymptote, see how this little auxiliary graph cuts into the x-axis, like it has x-intercepts? That's where you'll drop the asymptotes. And then see how it's got a max and a min on that little auxiliary graph? When it maxes, open the parabola that goes up. When it mins, open the one that goes down. End of story. So what I'll really be doing when I show you those is we'll be practicing more of what we just did in section 6.4, how to build a sine and cosine graph. Because if you can do that, you can get those 2 piece of cake, because you'll just be using the other thing and additionally dropping asymptotes and then opening up these parabolas. You're going to be asked domain and range here. When they ask you for the range, now you can see that there's a domain for both of these, that if I had the paper and the time, that those graphs go on and on in this direction and in this direction. So the domain is, when you're reading the domain to somebody, you're going to say it's all real numbers, except, because if you don't remember what asymptotes are, asymptotes is for where the graph is undefined. Like if you were to put that value, take the value where you see this asymptote, see it's at 1 pi. If you were to take that and plug it right in here, your calculator would shut down on you. It would say quit, just wouldn't be able to do it. So every time, now this is from algebra, every time you see asymptotes in a graph, those are x values that are not in the domain. When I say undefined, I mean they are x values that would shut the function down if you were to put it in a calculator. So if you want to speak about domain here, because they're going to ask you this in almost all the problems, you would say x is all real numbers except, you would put a comma and talk about the exception. Except the numbers where the asymptotes are. And you're going to see that they're going to try and draw out of you, do you see where those asymptotes are dropping? Like, do you see, let me blow this up, that the values that it's undefined at for this first one, just so we can talk in the language that they are going to try to elicit from us. All right, so for instance, if I was trying to talk about this domain, I would say it's all real numbers for the x, except, do you see that the asymptotes are dropping out? 1 pi, 2 pi. And if this thing went, you'd have one at 3 pi, 4 pi. So what do you call those? You look at the coefficient. This one's 1, this one's 2. So you can't use the word odd, because this number is 1, this one's a 2. But you can call those integers. So you will say the domain is all real numbers except integer multiples of pi. And you talk about the exceptions. Anything that's got asymptotes means you may not use that x value because it's an undefined value. Same thing here. Only here, look at the asymptotes. They're not in the same place. This is the cosecant graph. For secant graph, look what's happening here. That's 1 pi. That has to be half a pi. So it's half a pi. This is 1.5 pi, also known as 3/2. So at 1/2 pi, 3/2 pi, notice you got the same thing going on here. You have an asymptote at -1/2, -1.5, which is 3/2. So these are called odd multiples of pi over 2 when you talk about the exception. Okay, you'll start off saying the domain is all real numbers except odd multiples of pi over 2. They're going to try, and if you've looked at the problems, you probably haven't, but as we go through them, you're going to see that that's part of a lot of the questions. All right, that's those two graphs. I'll show you an easy way to graph those. Tan and cotan, we're going to have to use the patterns here. So you're going to have to know the one for tan, know the one for cotan, and I'll tell you right now, one of these, tan or cotan, will be one of the ones you do by hand with no calculator. You'll put your calculator away. You'll get that part of the graph. Make sure you memorize those two patterns. Make sure you memorize the cosine and sine. I can get you out of secant and cosecant. Make sure you know these patterns. So it's middle up, A. Now we got an A in our patterns because these graphs, all in this section, they all have asymptotes. So whenever you see an A, that means drop an asymptote. Okay, we'll be doing most of the same thing that we did in the last section. Now, did you see that when I did all the graphs last time? We were together, that whenever I started, I usually started with a period, and it always started with 2 pi. Everything's got a period of 2 pi, and if you don't remember what period is, also called a cycle. It is the distance between which you have to plot 4 points and start right back where you began. That's called a period. And did you notice that all the patterns I've given you thus far, only 2 of them, have 4 letters? And that's what a period is. Within a period, you must plot the 4 points that go with the 4 letters of the pattern. Okay, well, what I want to point out to you for these two graphs, tan and cotan, they're the only odd ducks. Instead of having a 2 pi period, they have a 1 pi period. So you're not going to start with 2 pi, you're going to start with 1 pi. You have to memorize that. Everything starts with 2 pi except tan and cotan. And it probably says that here. Okay, so you can put it right here, although that is what this means. You're going to start, when you do the graphs, with 1 pi rather than 2 pi divided by b, and that's for tan and cotan. These I could get, like I said, I could just get you to graph these by knowing how to graph sine and cosine. So you're going to start with the same kind of period you would start on with a sine and a cosine. Because, you know, everything is based off the period, so I always start by finding that. Okay, now I'll be graphing towards the end of the section. Right now, towards the beginning, it's like they always do it. They want you to look at some pictures and see if you can answer the questions and understand the terminology. Okay, flip over here. This is cotan. Now notice the difference between tan and cotan. Because I noticed when I looked at the problems in my math lab that there was a lot of multiple choice. I do have some multiple choice on the test. I'm just giving you some hints about what's on there. Although the practice test is a major hint of what's on the real test. It is just like the real test, only there's more problems on it for you to practice. So the main thing between this and the one that was on the previous page, look, this one goes up. It increases as you move to the right of the graph. So this one kind of increases as you move right on this picture. And the one that's on the next page, it goes in the opposite direction. So if you see that you're doing a multiple choice graph, sometimes that alone will help you to pick what the answer is. All this stuff that I've been doing with you where I fully developed the graph, I don't care if you go through all those steps if it's multiple choice. If you feel that of all that stuff that I laid out before we did the graph full blown, if you feel like you can get away with just doing a couple of pieces of that and then picking that question, go for it. But if I'm asking you to do the graph from start to finish, full-blown graph, then I want it all. But if it's multiple choice, I'll let you get away with using your calculator if you want, jotting a few things on paper, because the calculator doesn't always give you the detail that you want. But you'll see as we do the problems now what you can get away with when it's a multiple choice question. Okay, so notice that this one climbs upward and to the right. I'm talking about these little waves right here. It's got asymptotes at odd multiples of pi over 2, just like this graph right here, that's talking about the asymptotes. This one goes in the opposite direction, and it's got multiples of, integer multiples of pi. See, there's at 1 pi, there would be one at 2 pi, 3 pi, and so on. I want you to get the trig function just like I taught you in 6.4. Always get the amp happening out front, right after the trig word, but right before the x. So wedged in between the trig word and the x will be the b value. You go pluck that out and do your period. Let's see, what else? These will be, this is a horizontal shift, but that builds right into the pattern. So if you know how to use the pattern, it's going to roll right into there. One thing I do want you to notice, you're going to have to pay attention to it a little bit more, only because now we're going to do tan and cotan. All right, so tan and cotan. You know how tan and cotan, they max out at a certain height and they min at a certain depth? Tan and cotan don't do that. They go like this. So what do I call upper? What do I call middle? What do I call the downward step? I got to know where those steps are, or else I can't use the pattern properly. So I want you to know in general, the x-axis is always the middle level, unless there's a vertical shift. You guys know what a vertical shift is? That it takes the graph and picks it up? Well, if there is a vertical shift, it doesn't only pick the graph up. Those 3 levels that we've been installing right before we got ready to graph, upper, middle, and downward, it also picks those up. So if I'm telling you, because on tan and cotan, you got to have a better understanding of upper, middle, and downward, only because it doesn't have a max and it doesn't have a min. So basically, do you see that this number all the way at the end, not trapped in parentheses with the x, all by itself, it's a constant. If there happens to be one of those, that can affect the middle level. And you're going to see me do a problem like that. Middle's always at x, the middle level. But if there's a vertical, like let's say there's a +2 at the end, see if there's a +2, then instead of the middle level being at the x-axis, you're going to pick it up 2 units. Whatever the number is out here, it affects all of the shelves. So why don't you just think of the middle shelf? It's always at the x-axis unless there's a vertical shift. You don't have to really think about it for any of the other graphs because we're doing it off of sine and cosine, and sine and cosine have a top and they have a bottom. They top out, they bottom out. That is not true for cotangents. You have to understand the significance of a vertical shift. You'll see me do one like that, and I'll point it out again. All right, let's go. Let's roll. We're going to go to these problems, try to figure out what in the heck they're asking. I'll try to get the answers in the right spot. Sometimes I don't notice that they're giving you the blank spots for the same question. Just I'll answer at the bottom. Okay, so let's see. All right, look at the tan graph, and we're going to answer these questions on the tan graph. Go find the tan graph. It's on the bottom of the first page. All right, so do you see that tan is symmetric with respect to, all right, now let me give you something. I think I want you to write this in here. I mean, we could have written it in 6.3. In 6.2 and 6.3, do you remember me talking about odd and even functions? Why don't we transfer that information here, because I want to drag in the word symmetric so that you remember things that you should remember. Okay, first of all, why don't we talk about the two that are even? Do you remember what two trig functions are even? Cosine, and what other one? All right, and this is what it looks like when somebody's trying to say something is even. They tell you that even if you plug in a negative, it comes out the same as if you had just plugged it in without a negative. So that property is true for secant and cosine. I'm just reminding you of formulas and properties I gave you in 6.2, and then I copied them again in 6.3. These are the even functions. Okay, let's see if you remember this. Let's drag it into your algebra. You know that this is an even function, right? See, in algebra, they were a lot easier to identify because even was just something that had an even power. Well, when they're even, classic parabola, don't they wrap around the y-axis? Like here's the y-axis right here, and you got one leg here and one leg there. Okay, so that is a property of any even function, even if it's a trig function. When something is even, and I want you to know this so that to cut down on the work. Like when you left the other day, you were telling me that very, very long problem where we tried to figure out when this line called negative 4.5 ran into the cosine graph. And you were saying to me right at the end, hey, we got those two negative ones in degrees, and we were fussing about the degrees and the radians. And you said, hey, can't I just get the other two just by taking away the negative sign? You could have, because that thing was a cosine. I don't know if you guys remember what we were doing, but there was a cosine graph. There was a line that went right through it, and I was trying to teach you how to use the intersect function. Where does one intersect? So we had found two negative answers over here, but wasn't there a third and a fourth one here? Anyway, because the cosine's even, if you had, and the answers, I remember them, were negative 240 and negative 120 degrees. That means positive 240 and positive 120 are also answers, because this is what's true about even functions. They have, number one, y-axis symmetry. And I mean, this has to do with what we were doing the other day before you left. We were looking for some answers that were over here that were negative 240 degrees and negative 120. So you could have just come over here and got the two positive counterparts. So it is said that when you're talking even functions, any even function has symmetry with respect to quadrant 1 and 2. Let me help you understand that. With respect to quad 1 and 2, and then I'll drag it into the problem that we're doing now. In other words, if you know a point right over here in quad 1, and you don't want to do any further work to get the answer that's in quad 2, all you have to understand is this. If this point was called xy, and I was looking for its mirror image, because when you're graphing parabolas, a lot of times you use a point that's right across from it. If this is called xy, its symmetrical mirror image is called negative xy. Let me see if I could squeeze this in. Negative xy. That's what it means to be symmetrical with respect to quad 1, 2. That if you have any point on the graph called x and y, just switch the sign on the x, do nothing to the y, and you have two answers. One in quad 1, one in quad 2. And that's what I was discussing with her when you guys were on your way out. Okay, so that's going to be true of this and this. Odd functions, which is what we're talking about in this very first question that I have not answered yet. Tan's an odd function. Okay, let's remember some things about odd functions. Odd functions are going to be tan, cotan. They're the ones that are like this, that if you see a negative right in here, you got to keep the negative, and then you can make that theta positive. Let me move this over so I'm not running off the paper. Cotan also has that property, that if you see a negative right here, you got to keep the negative. You got to float it out to the front. Okay, so anyway, tan, cotan, who else? Cosecant, because cosecant has to do with sine. Sine is odd. Cosecant's another one. And sine. So almost all of them except cosine and secant. Okay, odd functions. Let's talk about an odd function that you're probably familiar with. Y equal to x cubed. Looks like this. Look at the symmetry going on here. Most students understand the parabola symmetry, but they have a hard time understanding this one. But things that are symmetrical, because they're odd. Anything that's odd has what's called origin symmetry. Okay, when you're talking about a point that's here, you will be able to find its symmetrical point down in this quad right here. So we say that anything that is considered odd has what's called origin symmetry whenever you have matching symmetrical points in quads 1 and 3. So write all of that next to your odd functions, right? Points are symmetrical points in quads 1 and 3. So in other words, if you know a point right here called xy, you will find its symmetrical point down here, and it will be negative x, negative y. I mean, you can be sure that if you know it's odd, and you know one point in quad 1, don't bother with the more complicated quads that have all the negatives. For sure, that point is on the graph. And that sometimes really cuts down on work. So you have symmetrical points in quads 1 and 3. In other words, if you have a point in quad 1, you can be sure that there is a symmetrical point in quad 3. Everything in quad 3 has got a negative x and a negative y. Okay, what is that called? Origin symmetry. What is this one called? Do you see anything that's got symmetrical points in quads 1 and 2? Do you see that this is the y-axis and the parabola wraps around the y-axis? This one's called y-axis symmetry. That one's called origin symmetry. I'm reviewing all your algebra with these so you can apply it to what we're doing now. Okay, this is called origin symmetry. And that is for anything that is an odd function. This picture right here, this is called y-axis symmetry. And that's for anything that is an even function. All right, let's go and answer this question now. All right, so we know that this is odd. Maybe put that so you can relate it to what I just spoke about. And when it says, is symmetric with respect to what? Well, all odd functions are symmetric with respect to the origin. It's called origin symmetry. That's what you're going to fill in right there. That means they have symmetrical points in quadrants 1 and 3. So we're going to fill this in with origin. And then it says n has vertical asymptotes. Okay, go look at your picture. Vertical asymptotes, you're looking at the tan graph. Where are the asymptotes? Are they at integer multiples of pi or odd multiples of pi over 2? Odd multiples of pi over 2. So you just look at the picture, and you're going to go, we picked origin for our first answer, then we picked odd multiples of pi over 2. All right, go to number 2. Now I want you to look at the graph of secant, but before you even look, is secant odd or even? It's even, right? Okay, so what's the symmetry that it's called that it has? All even functions have what kind of symmetry? Y-axis. That means, now you can't see a true wrapping when you're doing a secant graph, but you really can. I just haven't developed it for you. But on either side of the y-axis, you will see same things happening in the graph when we get to it. Okay, so it's symmetric with respect to the y-axis. And it has vertical asymptotes. Look at your picture. Where are the vertical asymptotes on these? Because what I showed you is the parent graphs. They're not shifted or anything like that. So where did they fall for that? Odd multiples of pi over 2 or integer multiples of pi? Okay, integer multiples of pi. All right, and everybody's looking at that. See right here. Let's see if we agree with her. What's going on for secant? Because that is what we're answering a question about, right? Here's one asymptote. Where is that asymptote? What is that showing you? That's at 1 pi over 2, or is that at 1 pi? That's pi over 2, right? Because you see the pi right here, don't you? Isn't that the halfway mark? So even though they chose not to label it, you label it if you want, because they did label it in some of these other diagrams. You can label it pi over 2. So it's got an asymptote at 1 pi over 2. This is what, 1.5? That's 1.5 is the same thing as 3/2. I see odd multiples of pi over 2 happening here. So back to that question. Y-axis symmetry, odd multiples of pi over 2. You can just look at the pictures that I've given you. Number 3. What is easiest to graph? Remember I told you I was going to get you out of using a brand new pattern for secant? You're going to graph the thing that's reciprocal to this cosine. So when you graph this, I really want you to graph this. And I'll show you just how to do that and how to then turn it into a secant graph. So answer here, graph cosine. And because cosine is reciprocal to secant, we're going to build it off the cosine graph. Number 4, the graphs of tan, cotan, secant, and cosecant have infinitely many vertical asymptotes. Yes, that's true. Look at the pictures I've given you. Of course, they only give you a shortened version of the picture. They only have so much paper, and they're trying to finish it, put it in a small space. But really, those graphs go on indefinitely. Therefore, the asymptotes go on indefinitely. So true for that one. Okay, what is the y-intercept of tan? Let's see if you know what that word is. Go to the picture for tan. What is the y-intercept if you even think it has one? Because you could answer B. 0, 0? That's it. These are simple at the beginning. And you could put it like this, but I think what MyMathLab wants is just the actual, what is the y value at which it hits? So it probably just wants that right there. Okay, number 5. Well, that was 5 and 6. All right, now I want you to stay between negative 2 pi and 2 pi. Does the graph have any vertical asymptotes between negative 2 pi and 2 pi? Go look at the graph, and let's see if you can tell me what the answer to that is. I'd rather you do it yourself, because if you're just feeding off of my answers, I'm the one doing all the hard thinking. Go look at the graph and see if you can figure out what the numbers are, if any, because maybe you don't think there's any. Keep your vision only looking between negative 2 pi and 2 pi. What are the vertical asymptotes? You're not calculating anything. You're not building a graph. All you're doing is looking at the picture. Where do they hit? Negative what? Negative 3 pi over 2? Is that one of them? Are there any others? Because if they're asking me for all of them, I need to put all of them. Anything else there? Negative 3 pi over 2. Pi over 2? Negative pi over 2? Okay, plus and minus. So you're saying, now wait a minute, this thing that we're looking at is tan. Okay, so you said it hits at, and let's check. I agree with what I'm hearing, but we'll look at it anyway. What are we doing, tan? We're looking at this one. Okay, so we're looking at that one right there. That's this problem. And yes, it hits at 1 pi over 2, 3 pi over 2. And the fact that you guys were really thinking about the negative ones, that's good, because they didn't really show you much of that. Doesn't mean it's not there. Okay, if you're considering all the way to negative 2 pi, and we just talked about how the asymptotes hit at odd multiples, and that means there's one that they're not showing here. Because here's 1 pi over 2 in its negative form. So negative 3 pi over 2. Anything that's got an odd number at the top but a 2 on the bottom is going to be an asymptote. So we'll say negative 3/2. You can they showed you the negative 1/2. And then if we're allowed to go all the way to 2 pi in mentioning our answers, then this one's also valid. And this one they showed you. Okay, the only one they didn't show you was that one. So you have to understand what we just discussed in previous problems. Any odd integer multiple of pi over 2. All right, let's go to number 7. Now, if I can get out of doing work here, I'm going to. So let's look at these problems. First of all, why don't we rule out the ones that are just, there's no way it could be that. Okay, get your head thinking. Maybe go glance at the tan graph. Doesn't the tan graph go like this? It increases as you're moving to the right. Therefore, which ones should I rule out? Because they're not even going in the right direction. Okay, D's no good. It's climbing to the left. So I have to consider all of these. All right, let's check this out. Why don't I just do the period? Because I'm not sure I'm going to build that graph if I don't have to. That's a lot of work. I'm going to start with the period. Now, remember I told you that tan and cotan are the only ones that start with 1 pi, not 2 pi? Okay, so the formula instead of 2 pi over b is 1 pi over b. Get your eyes right in here. There you go. Right in there is the b value. So it's going to be 1 pi divided by b. And then remember how to deal with this. Whenever you're doing a fraction divided by another fraction, float and flip. Float the bottom fraction to the top, flip it over, and then it becomes multiplication. So dividing by pi over 11 is the same thing as multiplying by its reciprocal. And when you do that, this becomes pi over 1. This is just pi over 1 because now this fraction is up here. And you're multiplying it by 11 over pi. So you get 11. I want you to take that 11 and see if you can pick the answer. Because I think it's enough to help you pick the answer. I mean, they're telling, look at what they say up here in the directions. Let me point it out to you. Do you see that you're supposed to provide at least 2 cycles worth of a graph? All right, and did I not say that a cycle is the same thing as a period? And if what's a period? That if you were going to do the graph, you would do the pattern, the 4-point pattern within that period. Period's a cycle. So if you know that one period is 11, what do you think the answer is? And you understand that why A and B are no good? See if you can verbalize why A and B cannot possibly be the answer. There's something that they did there that gives it away. X-axis, right? Did you see how they put those pi numbers there? Our x-axis doesn't have any pi numbers in it. The pi got wiped out. Because the b value had a pi, when we flipped it over, it wiped the pi out and left you with just plain numbers. When the b has a pi, you will just have plain numbers on the x-axis. So, can't be this. Why? Because of these pi numbers. Can't be this because of the pi numbers. And we already ruled that one out. So if you don't have to fully do the graph, don't. Even on the test, jot out what you have to do to finish the answer. Okay, maybe you want to write here that 1 period, which is equal to 1 cycle, is equal to 11. Therefore, this thing that shows 22 is 2 cycles. It's an 11 and then another 11. All right, let's see if we can figure out what's going on here. All right, use the graph to determine the domain. Okay, so domain is all real numbers, but I want to talk about the exceptions, where the asymptotes are. So look at that tan graph again, that parent graph. Where were those asymptotes happening on the tan graph, or the parent graph? Was it multiples of pi over 2, odd moles of pi over 2, or was it integer multiples of pi. Which one was it? Pi over 2 deal? Yeah? Pi over 2? Okay, because that's how I'm going to set it up. If I know that in a parent graph, before you start changing the b value and changing things, because this graph will stem off the parent graph. So if I know in the parent graph that those asymptotes happen at pi over 2, I know pi over 2 is a situation where tan is undefined. So how do you drag that into this problem? You're going to take what they have right here. I'm doing this part. And you're going to figure out when would that possibly be equal to the undefined values on a parent tan graph. When is that? Because if this ever turns out to be equal to pi over 2, the whole thing is going to be undefined, which is where the asymptotes are. And when somebody asks you about domain, they're asking you about asymptotes. They want, because asymptotes are the x's that you may not use. When you tell somebody about domain, you got to tell them what x can be as well as what it can't be. Those are called exceptions. So right now, I am finding where this graph hits those exception values. What are the values that x cannot be equal to? Okay, so now, remember, you want to divide this right off of here, pi over 11. I want to divide this side by pi over 11. But when you're dividing fractions, you leave the dividend alone, you change it into multiplication, and flip over the divisor. So now the pi's would cancel, and you get this 11 over 2. So what I'm saying to you is that any time that you are in some multiple of 11 over 2, you are going to kill that whole function. It'll be undefined. We just found out by knowing where the parent graph is undefined and setting whatever they gave me here to that forbidden value on the parent graph. So what's the only answer it could possibly be? Has to be C. This means multiples. When they put a k off to the side, that means multiples of 11 over 2. It's the only thing that you can't be equal to. In other words, those are where the asymptotes are. Okay, for the graph, what's the range? Remember, range means how high does it go? How low does it go? What's the range for tan? All real numbers, right? Because it goes infinity, up to positive infinity and down to negative infinity. Cotan. Again, this says give at least 2 cycles, in other words, 2 periods. So why don't you just find out what 1 period is? Because I might be able to rule some things out here. Now, not for reasons of period. Are there any the graphs here that are blatantly just not the answer, having nothing to do with period? Which one? Okay, so cotan, we're supposed to be going up like this. And this one doesn't go in the right direction. So we'll cross that out. We're not even going to consider that. And then we'll see if we can handle the rest of the problem by process of elimination. Let's at least get the period. Not that we're going to do a full-blown graph. We're not ready for that yet. Let's do period. Okay, so for tan or cotan, you start with pi over b. The b value is 1/5. It's just the number, not the x. So 1/5. To simplify something like this, you float and flip. Okay, float this entire fraction up to the top and flip it over. And therefore, it is not on the bottom anymore. It's now at the top in a way that you can deal with it. Pi over 1 times 5 is 5 pi. Now, that may be all we need. That's 1 period. Do you see, is there a graph here that you think that you want to work with? What are some, well, what else can we rule out at this point? We can rule out C and D, because 2 cycles are not 2 pi and negative 2 pi. Bam, we found the answer already. Get away with it if you can. Can't be that. because these are not appropriate numbers here if I'm going to follow the directions that said 2 cycles. So it has to be that. We're going to build one start to finish, just not yet. Okay, this thing right here. What is the domain? Okay, I already know that the domain goes on and on and on. Except at the asymptotes, I got to find out where the values are. What are the values at the asymptote? Now wait, for cotan, please go look at the cotan graph. And tell me if you could see where the asymptotes were on that parent cotan graph. Were they integers of pi, 1 pi? Yeah, that was the 1 pi deal? The 1 pi, 3 pi, 1 pi, 2 pi, 3 pi? Okay, so let's just go with 1 pi. Let's keep it simple. Let's keep it positive. Let's do the very first one. All you want to know is working off the parent asymptotes. You guys just told me that the asymptotes happen at 1 pi, 2 pi, and all the negative versions of this. I'm just going to go with this one right here, smallest one, and I'm going to work it into this problem. I want to know what would possibly make 1/5 x equal to any of these forbidden x values. Forbidden x values are things that make the function undefined, and therefore there are asymptotes there. So I'm trying to find that situation. When is this equal to, I could have used anything here and I would have gotten the same answer, but why not just go with the smallest one? Okay, now solve it. Okay, get used to getting rid of fractions. You can divide the whole fraction off of there at one time. Likewise on the other side, you're dividing by 1/5, but don't forget, when you're doing division, and either one of the things, the dividend or the divisor, is a fraction, leave the item in front of the division sign alone, but flip over the divisor. Oh, we had already, oh, no. We got 5 pi. All right, so which answer do you think it is? So we just figured out that if we go and plug in any multiple of 5 pi, look, we don't ever want this to be equal to pi. You just said the asymptotes were at 1 pi, 2 pi. We don't want this to be 1 pi. If I was to put 5 pi right in there, 5 pi divided by 5, 1 pi. If you put anything bigger than that, you'll still be at multiples of pi. So do you know? Can you pick the answer from there? What do you think it is? Just B. Okay, all you're saying is any multiple of 5 pi. Like even 10 pi would ruin it for you. If you were to put a 2 in there, what I did is find the smallest one. But if you do 2 times 5 pi, 10 pi. Put a 10 pi in here. 10 pi divided by 5, 2 pi. Isn't it true that on the parent graph there's an asymptote at 2 pi? So any multiple like that. All right, so now let's do this. What is the range? All real numbers. Okay, let's get to 9. All right, I got a half an hour to graph. Ready? Okay, secant and cosecant, we're going to build it right off of what you were doing in section 6.4. So let's practice again what I taught you. There's a lot of negatives in this section. So remember I was telling you how to take mum-d and dum and make them flip over? You just switch the u's and the d's. So let's practice more of that because I notice there's a lot of negatives here. Okay, here we go. All right, so who is reciprocal to cosecant? Sine. So you know what you're going to do? You're going to replace the word cosecant with sine. Okay, let me write it right here. Reciprocal of cosecant is sine. So we're not going to write it as a reciprocal. Just know which one is the reciprocal partner to this. Rewrite the equation. We're going to actually graph y is equal to -3, replace the word cosecant with the word sine, and use everything else that's in the problem. Okay, here we go. I think before you get all wrapped up in the calculations, period, jump, all that stuff, why don't we flip the pattern first? Because students always forget to flip the pattern. Do you know what the pattern is for sine? Mum-d. Mum-d. M-U-M. Let's write that first. I mean, I don't suggest you do it in your head. I like you to write it on paper. You don't have to. That's the original. Now let's flip it. All we're going to do is switch this and this. This will be a D. This will be a U. You cannot switch the M's. I would make sure that I'm paying attention to that, and I would cross out the original at that point. We're going to use this pattern when we do go to graph. All right, now let's start doing the calculations. Period, jump, put our shelves in place, okay? Practicing everything we did the other day. Here's my period. What do I start with, 2 pi or 1 pi for this one? They're all 2 pi except tan and cotan, okay? So 2 pi. I look for the B value. There he is right there, squeezed in between the trig word and the X. Then I learned very well how to deal with this. Just float this up to the top and flip it over. So it's not there anymore. Now we just say that what's underneath the 2 pi is now 1. There it is up at the top. We have a full period of 16 pi. But my period is used to help me design my x-axis. And what I need to design the grid marks is the jump. So when I want the jump, I go like this. The jump is the full period divided into 4 parts. So what was the period? 16 pi? 16 pi divided by 4. Now some of these you could get away with not doing the whole graph like I said, but we've already practiced enough of this and I have to have something to practice the graphs with. So let's do the whole kit and caboodle here. All right, so we got the jump. That means my grid marks are going to be spaced out, my scale, every 4 pi. So I'm going to have 4 pi, 8 pi, 12 pi, 16 pi. Likewise on the negative side. What else could I do? Start point. I need an anchor point to start this because the anchor point serves as the first letter of the pattern. So next is start point. Come right here, or you could call it starting position. Start point. You're going like this. Let's recall this from the other day. You're trying to plug whatever is necessary in for the x that will create a 0 in this thing called the augment. Okay, so that would just be a 0. And remember, we're using this function right here. You're doing everything for this function. Okay, once you rewrite it, you use it until the end of the problem. Okay, so it's y is equal to -3 sine of 1/8 times 0. Putting a 0 right in there will zero that whole thing out, and you want that to happen. That's the easiest start point you could find. Okay, so here I come. I'm going to write my start point. I plugged a 0 in for x. I'm now going to put that in the calculator, but, you know, clean it up a little bit. This is what you should enter in your calculator. 1/8 times 0, 0. Just put that in. Now, some of you are going to start being able to do this in your head. Sine of 0, that means what is the sine value at 0 degrees? 0. 0 times -3, 0. But you can just rely on your calculator. Okay, you will get a 0 if you put this in your calculator. Not where the y, don't put it where the y is equal to as though you're graphing. Just like enter it like a calculation. Okay, we're going to start at 0. Okay, let me remind you of the pattern. Why don't we bring the pattern right up underneath here? It was M, D, M, U. This start point is where you are with whatever is the first letter. Look at the first letter, because that first letter signifies what level you're at with respect to the start point. And then you continue using the pattern. So the next letter in the pattern you're going to use is down, because the 0, 0 will already be for the middle. Okay, now let's graph. We have everything we need to graph. Come down here. Yeah. Okay, so your work there says that every 4 pi I'm going to put a little scale mark. Okay, so 4 pi, 8 pi, 12 pi, 16 pi. Get the same thing on the other side. 4, 8, 12, 16. Now, if you've done the homework, today probably seems a lot easier than when I first threw all this stuff at you, because now you've probably practiced a few of them. Okay, after I put those little grid marks, what did I do after that when we were graphing the other day? Yep, put the shelves in there. Put your upper, your middle. Okay, now wait a minute. We did the start point so we would know what level we were at. So what we were at, 0, 0. And supposedly 0, 0 is at the middle level. And I'm telling you, the x is always the middle level unless you have a vertical shift. You know where you can find the vertical shifts? It'll be a number that's added right out here. Like if it's a +2, everything's 2 units higher. If it's a -2, everything's 2 units lower. But I don't have anything there. So the middle is the x-axis, just like we already knew. Put m there for middle. And then how do I know where the upper level is with respect to the middle? What number do I use to figure that out? The 3, the amp. Okay, amp. I know it's a negative out there, but you use it without the negative when you're figuring out the spacing. So 1, 2, 3, go right up there, and that's where your upper shelf is. And then amp it down. 1, 2, 3. So that the spacing between all of these shelves is 3 units. All right, so I already have my anchor point, my start point. I've already done M for that. Let's look at the pattern. We're going to go DMU, down, middle, up, down, middle, up. All right, so let's see. If I'm going to go down, I got to slide whatever the jump is and go down, just like the pattern says. Then slide whatever the jump is. You're always sliding the same jump. And the pattern now says go to middle. Not that you don't know that, because if you've hit rock bottom, you have to start going up. Slide 4 pi, all the way up. Slide 4 pi, start coming down. Slide 4 pi if you want, all the way down. Start connecting the dots. I'm just putting this here because I don't want you to think that that is the real graph. Okay, I'm going to get some more over here. Let's see. There'd be a point here, point here, point here, point here. Okay, ready? Let's put the asymptotes in. Do you know what x-intercepts are? Everywhere what I have drawn just now hits the x-axis. Everywhere that it hits the x-axis, at each of your x-intercepts, drop an asymptote. Okay, where the auxiliary graph, just the thing that guides the real graph, where it peaks out, maxes, you'll have your parabolas that open upward. Keep them squeezed inside of their asymptotes. Don't break through the asymptotes. Okay, so we have an upward here and here. At the maximum points, do the parabolas that open up, and at the minimum points, do the parabolas that open down. Okay, and then you got a nice, beautiful graph. Now answer the questions. Okay, look at the graph and answer the questions. All right, what do we have here? It says, well, first of all, we got to pick the graph. Which one do you think it is up top? Now look at the position of your parabolas. Do you see that the thing that's going to help you to pick out which of the graphs it is? Do you see that there's one on the left side of the y-axis and one on the right side? I think there's only one selection there that has a graph like that. Which one is it? A. Okay, it has to be this one. None of these other ones are doing that, with one to the left and one directly to the right of the y-axis. Okay, let's do the next one. Use the graph. We already did the graph, okay. Determine the domain. What is the domain? It's everything except where the asymptotes are. Where are the asymptotes occurring? They look like multiples of 4 pi, or are they multiples of 8 pi? What's going on with those? What do you think? They look like multiples of 8 pi, right? Because don't we have one at 8 pi, 16 pi, all of that? Okay, and then look here and see what we have. That which answer here do you think is the answer? C or B? See the little k there? That means multiples of 8 pi. I know they wedged it in the middle. I don't know why they want to annoy you like that. It's usually at the end, but that's what that means, multiples of 8 pi. Because look, this doesn't say 8 pi. That doesn't say 8 pi. This is the only one, and it's definitely not all real numbers. Because at the asymptotes, those are x values that are not in the domain. And if you don't know how to read these, because, you know, when you say it verbally, you say to the person, it's all real numbers, except it's not, and then you talk about the exceptions. So when you're given an answer like this, what you see right here is a statement of what it can be, and what you see on the other side of the line is a statement about what it can't be. Domain, you're always talking about what it can be and what it can't be, if there's exceptions. There are exceptions. That's how you read this. This is said, all x's, every single x value except, and then over here they start talking about the exceptions. Okay, go to the next page. Let's go to secant. Let's try this again. All right, so that's reciprocal to cosine? Yeah. Okay, what do you think the range is here? Yeah, do you see? Oh, by the way, if I didn't say this already, I think I did when I gave you these same graphs in 6.3. But if I didn't, you're only supposed to be answering with respect to these guys. Did I say that in a previous section? Not with all the stuff that helped you get them. Okay, so these parabolas are at, what is this, 3? 3 and higher, or 3 and lower. Only answer what the range is with respect to the parabolas. Okay, so that would be this. Their y values, which is what ranges, are either greater than 3 or less than -3, because that's -3. This is +3. You can answer everything off this graph. Okay, secant. Secant is reciprocal to cosine. So we're going to use the cosine so that we don't have to memorize a new pattern for secant. All right, so we're really going to pretend like we're graphing -6 cosine of pi times x. Okay, let's go for it. I think you should do the pattern first, just because it has a flip and you're going to get all wrapped up in doing the calculations in the graph. Okay, so let's see. For cosine, it's a thumb down. That's before you do anything to it. So write it down real quick. Then flip it, switch the U's to D's and the D's to U's, but put the M's right where they were. Cross out the old one. Maybe highlight the new one so that you don't accidentally go back to the old one. Start doing the calculations. Period for sine, cosine, secant, cosecant is 2 pi divided by b. In this case, it would be 2 pi. There is your b value right there. It's a pi. Therefore, my entire period is 2, and therefore my jump, which is always the entire period cut up into 4 parts, is 1/2. Whoops, let me put it right here, and then I'll reduce it. Now I'm going to graph the whole thing again for you. Okay, so here we go. Let's see what else. Let's do start point. Okay, start point. Remember, you want to zero out that augment. That is right there. The number that you would plug in right there to zero that out is x is equal to 0. So start point. Remember, we're using this function. Once you rewrite this, only look at this. Don't look back at that anymore. You'll get too confused. Okay, so what I'm going to plug in for x is 0, and then maybe I'll get my calculator to help me with this part. -6 times cosine of pi. I'm putting in a 0 right there, which means this whole thing is zeroed out like I wanted. Okay, put that in your calculator if you need to. If you're doing it in your head, cosine of 0 is 1. 1 times -6, -6. You should get a -6 when you put that in. Okay, there's my start point. Okay, what else do I need? I need my start point with my pattern so I can start putting the shelves in there. So let me drag my pattern down here. I'm going to put my start point right here. I'm going to put the pattern right underneath it, DMUM. And I'm going to say that this start point is in the downward position. Okay, here's my graph. Okay, I'm going to label the x-axis based on the jump. Every 1/2 I'm putting a little notch mark. Do the same thing on the negative x side. I'm numbering using halves. 4 halves and 5 halves. Now I'm going to put the shelves in place. Well, I do that by doing the start point. My start point is at 1, 2, 3, 4, 5, 6, 0, -6. And supposedly that is the lowest level that you can be at. So that's the downward level. Where the start point is the lowest level. Then from there I use the amp to figure out where the next level is. So my amp is what, 6? So amp is 6. So says the -6 that's out in front. So I'll go 6 up right there. Just like I said, the middle is always the x-axis unless you have a vertical shift, and we don't in this problem. Then go up 1, 2, 3, 4, 5, 6. And at 6 you have the upper shelf. Okay, all my shelves are in place. Now you can start doing the pattern. All right, so I already did the first letter of the pattern. Now I'm going to do MUM, middle, up, middle. Okay, so middle, up, middle. And then you can just continue from there. Oops, I accidentally made them solid. That's okay. This would be down here. This would be down here. Okay, then here, if I was going to get some graph over here, I'd have to start going up, all the way up, back down to middle, all the way down, back up to middle. Okay, then right where the x-intercepts are, asymptotes. Okay, and then open up your parabolas where it maxes upward. Where it mins out, downward. Okay, answer the questions. What graph do you think it is? C is just, that's out of there. Why don't we look where our parabolas are? Don't we have a parabola that opens right on the y-axis, a downward parabola? Because this is your y-axis right here. Is there only one graph that's like that? D. Okay, so D has to be the picture. Let's see. What else are we answering? What is the domain? Which really forces us to talk about the asymptotes. Where are these asymptotes hitting? At 1/2, 3/2. Same thing over here. 1/2, 3/2, 5/2, but negative. So odd multiples of 1/2. Let's see if there's an answer like that, because I don't know if there is. Yep, this guy right here. This is like saying multiples of 1/2. If you throw a 1 right in front of there. Multiples of 1/2. So D for this. What is the range? Remember, only use the parabolas when you're talking about the range. So those ones that open up, aren't they 6 and above? And the ones that open down are -6 or less. So that would be this one. Okay, last one. I'm going to finish with a tangent. That's all I have time to do. Let's go to, let me pick one on the next page. Let's do 12. Okay, so 12, I can't give you an easy way. You just have to know the pattern. Go find the cotan graph and go grab the 4 letters that go with it, the pattern. Okay, so cotan's on the back there. Do you see that the pattern is AUMD? Okay, bring that over to this page. Let's do the period. Period's 1 pi divided by b. So 1 pi, my b value is right in there. 1/8. Float and flip. Okay, that's my period. I get the jump from the period. So you take whatever you get for the period, divide it up into 4 parts. Okay, no flipping happening here, so I leave that pattern like that. Okay, let's see what else. Start point? Well, I don't know that we really need to do the start point. Isn't the start point always, well, every time I do a start point, haven't I been trying to zero out the augment? Okay, so in this case, you tell me, what would I have to put right in there for x to make this whole thing turn into a 0? Just this part in the parentheses is a 0, right? Okay, now, haven't I said every time I've done a graph that the start point has to do with the first letter of the pattern? What is the first letter of this pattern? A for asymptote. So you know what's going to happen? If you were to put the 0 in and go and put it in your calculator, what would your calculator tell you? Error. It would say undefined. And that would make sense because the first letter of the pattern is A, meaning whatever that start point is that you're plugging in, you are going to get an undefined value. That's what asymptote means. So why don't you just put asymptote here? There is no value. It's undefined, but we do call undefined values asymptotes. Okay, let's graph. All right, let's see. What am I doing on the x-axis? Because that's what my jump is about. I'm going to go 2 pi. I'm going to go 4 pi. I'm going to go 6 pi. I'm going to go 8 pi. Likewise on the other side. Negative 2 pi. Negative 4 pi. Negative 6 pi. Negative 8 pi. All right, now here's a chance for me to finally talk to you about where you got to understand what vertical shift means. What number in this equation is a vertical shifter? The 1, right? And you know what that does? You told me yourself. It takes the whole graph and it pushes it up 1 unit. Well, it also drags those 3 levels. Now, hasn't the middle level typically been the x-axis? So why don't we just concentrate on that? The middle level is now going to be 1 unit up. Let's go install it. And from there, because it's too hard to use the graph itself to install it. So use the concept, and that's because they go on infinitely, whereas that wasn't happening in any of the other graphs. So think about your knowledge of that. Everything shifts up. So we're going to go up to 1, and we're going to put that in as the middle. Typically, the middle level is the x-axis, but everything is shifted up 1. Now go put the other ones in. Isn't the amp only 1/3? A little teeny tiny bit above, a little teeny tiny bit below. And you're going to have the upper, like let's call this 2. Okay, we already know that's 0. So if we go just a hair up, about 1/3 of the way, let me make this smaller. This will be my middle. This will be my upper. And then just go, down to here is 0, so just go about 1/3 of the way. That will represent your downward shell. So there's my 3 shells, very close together, but they're all stemmed off of the fact that the middle level is 1 unit up because of the vertical shift. Okay, so now, what was our start point? 0 asymptote. So go to x equal to 0, drop an asymptote. So at 0, I am drawing an asymptote. Okay, I already did the first letter of the pattern. I'm going to put the pattern right here. Okay, so I already did that. That was my start point. That's why sometimes we call it start position, because sometimes the first thing is not a point. It's something that you're drawing. In this case, an asymptote rather than a point. Okay, now we're going to go to this. All right, you know that every time we do something in the pattern, we slide. We slide over whatever the jump is. Our jump is 2 pi. So let's move 2 pi away from the asymptote and do what this says. Plot a point on the upper level. Let's slide again, 2 pi, and do what the third letter says. Plot a point on the middle